The second safeguard are these editing exonuclease activities that most or many different DNA polymerases possess. Okay. And so an editing exonuclease activity is an exonuclease activity that degrades DNA in the 3' to 5' direction. So an exonuclease is a nuclease that removes nucleotides from a nucleic acid, one nucleotide at a time from the end, right? Whereas an endonuclease, we'll be talking about endonucleases at some point in this course, are hydrolytic enzymes that cleave nucleic acid strands anywhere in the middle, right? So restriction endonucleases, for example. Okay, and so here is the end of a nascent nucleic acid strand. Let's say there's an error here, and so we want to remove this last base so we can try again. Well, the way that happens is that we can trigger a 3' to 5' exonuclease activity. And so in the exonuclease reaction, it's a hydrolysis reaction. A water molecule comes in, attacks the phosphorus atom of the phosphate group in the phosphodiester linkage. You then break the DNA by removing that last nucleotide. Okay, and now we've shortened the nascent nucleic acid strand by one base. Okay, we've removed this base. Okay, this reaction is not the reversal of the polymerization reaction, right? How can we tell, just from looking at these products, that this is not the reversal of the polymerization reaction? Yes?
It only has one phosphate.
Exactly. So if this was the reversal of the polymerization reaction, then one of the products should be a nucleoside triphosphate, since in the polymerization reaction, one of the substrates is a nucleoside triphosphate, right? And so, but when we attack this phosphate group with water, we only produce a nucleoside monophosphate. If this were truly the reversal of the polymerization reaction, we would have to attack this phosphodiester linkage with what? With pyrophosphate to produce a nucleoside triphosphate. Okay? And we wouldn't call that hydrolysis, we would call it pyrophosphorylysis. Okay. So this is not just the reversal of the polymerization reaction, so that tells us that it's probably not occurring at the same active site, because usually an active site can only catalyze one reaction. That's why enzymes are such amazing things. They're able to selectively react with a certain set of substrates to the exclusion of others, right? So the fact that this is not the reversal of the polymerization reaction says that it almost certainly occurs at a different active site than the polymerization reaction, and in fact, that's true. Okay, we know that's true from various kinds of structural studies on many DNA polymerases. Okay, and so the fact that this occurs at a different site is actually critical to the biological role of the 3' to 5' exonucleolytic reaction, because that's what allows us to trigger this reaction when there's a mistake. Okay, so we'll see how that works in just a sec. Okay, so here is what I mean by editing. So here's the template strand, here's the primer. The primer is being extended. And let's say that we make a mismatch. The DNA polymerase makes a mistake and incorporates some mismatch indicated by this little red part here. Okay? Well, that then triggers the polymerase to go into the degradative mode. It activates its 3' to 5' exonucleolytic active site. And so now we degrade the mistake. We degrade the DNA that contains the mistake. And now we can try again. We can flip back into the polymerization mode and try again and hopefully get it right the second time. Okay. So this editing will not increase the fidelity of this overall process unless there's specifically some way of triggering this exonucleolytic reaction when there is a mistake. If there's an equal probability of going into the degradative mode, regardless of whether there's a mistake or there's not a mistake, that's not going to get you anywhere. You need to specifically be able to trigger that degradation reaction when there's a mistake. Okay? And the way nature has found to do that is by using different active sites for the synthetic and degradative reactions. Okay? And this cartoon here basically shows how that works. So here is a Klenow fragment, and up here then between the thumb and the fingers then we have the polymerization active sites. There are two magnesium ions, not shown, that are right about here that are catalyzing polymerization. And let's say that the polymerase makes a mistake, so we have a mismatch here. Well, if there's a mismatch here, what's that going to do? That's going to weaken this duplex here. That's going to make this duplex here more likely to fray, to come apart, because we have a mismatch here that weakens the duplex, that destabilizes the duplex. Once this duplex begins to fray, now this 3' end can move down here into the exonuclease active site, which actually also contains a pair of magnesium ions that coordinate water and catalyze this degradative reaction. So by having two different active sites for polymerization and the exonuclease reaction, then we can specifically trigger the degradation when there's a mistake, because that mistake then increases the probability that this 3' end will find its way into the degradative active site.